Hey everybody, this is Larry. This is me doing Q4 of the Some of the Beautiful Subsequence, Q4 of the weekly contest 465. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. Yeah, and this one has a mod, so I don't know, don't forget, because I seem to forget a lot. But yeah, first things first, this is a very hard problem, at least for me. But also, honestly, I had all the components, but it's been a while, and this kind of shows you how like you have to practice. I haven't been practicing, and I think I solved actually like a easier version of this, but stuff that if I had been practicing, I would have been able to build on top of very quickly on this, and I was just not in shape. For this one, the first thing I want to go over is the GCD component. The subsequence part I think is interesting, but we'll go over that because I think there is a thing about for hard problems, and if you struggle with hard problems, and I struggle with this one, to be honest, so I didn't do this one well either, but the concept is still there, is that what you want to do is break it into components, smaller pieces that you can figure out how to solve, or even different pieces that enables you to, like basically you have a problem, you want to solve, quote unquote solve, you want to do something such that the problem is a different problem but slightly easier, and then do it again, and then so forth into components that you can figure out. Sometimes it's two things together and so forth, and this is hard, right? I mean, this is why a lot of people drop off at Q4 at Leetcode, or even like if you think about code forces, just more difficult problems in general. And like I said, just to be clear, you watch this, you're on YouTube, or I'm on YouTube, you watch this on YouTube's, it's very easy for someone on the video to sound smart. So be careful, but that doesn't mean, and I'm trying to, go over like, hey, it's hard, even for people who might been very practiced and experienced, and maybe even could have done it on a different day, maybe. Maybe I should not have been doing this farm at 5-6 a.m. That's another story. But in any case, yeah. So the first thing I want to go over is the GCD portion. I think this is the portion that I just struggled a lot with during the contest. Even though I've done exactly the same thing before, but for this one, like I said, some days you're just not, if you don't practice enough, some things you just don't see the connection for, and I certainly did not for this particular problem. So I am bringing up the drawing board. Right. I think the biggest thing to note is that the biggest idea here for me is that, okay, we have this idea of GCD, right? There are a lot of things to know about GCD, which makes it a little bit tricky, because some of them could be useful, some of them could not, or just not useful, right? Or not as useful for this particular problem. They may come in handy in other places, but not this one. I think the first idea that I would think about that connected the dots for me is not necessarily this idea. Well, okay, there are a couple of things actually. The first thing I want to say is that n is this is not related to GCDs. I lied, but n is equal to 10 to the 4th, and the maximum number is equal to 7 times 10 to the 4th, which is to say it's small enough to kind of get the divisors and stuff like that. You still cannot do n square, but even like n square root of n is fast enough, roughly speaking, as long as you're not like sloppy, etc. Right? And it turns out that within this range, and I could be lying on this one, / just Google, it's close enough, but I don't remember. Maybe I should have known, but which is that within this range of numbers, the maximum number of divisors is like 128 or something like that, or give or take, right? Which means that if you construct every divisor for every number, then that's still fast enough, right? And okay, so what does that mean? Now we have to figure out the reason why I'm struggling with explaining this a little bit is that I know the concepts, I understand the concepts, but also honestly not know and understand it in a well enough level to be able to convincingly maybe deliver this, right? But the thing you have to know, the thing that I thought about that worked for me in this problem is just this idea that we don't need to figure out the GCD yet. We can just figure out the CD, the common denominators, right? And or divisors, I suppose. Sorry. And yeah, and for each number, maybe I don't know, let's just say 100, right? Which is equal to 2 times, this is the prime factorization, but also the divisors may be, if you want to include 1, 2, 4, 10, I may be missing some, let me know, I wrote 10 twice, 25, 50, 100, right? So those are all the divisors, right? I hope I didn't miss any because that's embarrassing. But I think I missed 20 and 5, right? But yeah. Yeah, how did I miss 5? That's even one of the primes. Yeah. But anyway, my point isn't to, factor 100 anyway. But yeah, for each of these numbers, what does that mean, right? Not taking the LIS, the longest increasing subsequence example, is that let's say you have a list of these numbers. Well, yeah, let's say you have 100. 100 is all these things. That means that for each of these divisors, you could say there are one number, right? One number that divides on the list, right? Okay, so then you kind of break it up. So let's say you have another number, I don't know, let's say you have 100, which is just this one. Let's say you have another one, you have 10, so then now it's 2 times 1, 2, 5, and 10, right? So then I guess technically this is, I don't need to write 1 again, but 2, 5, and 10, right? And these are just all the possible divisors, right, as we know. And it may be, I don't know, 45, which is 3, 9, yeah, 3, 9, I can't just keep writing this, but like this. But yeah, that's 5, right? So it's going to be 3, 5, 9, 15, right? Something like that. Yeah, so you have another 3, you have 15 somewhere. You have a 9 somewhere, you have a 3 somewhere, right? All right. This is sloppy. But my point is that, okay, so you have all these things now, right? You have all these things. Let's say you go forward the list. You have all this built up. What does that mean? Well, these are the common denominators, right? And you could say that in English. And what I mean by that is that you just say it out loud. For example, the number 2, 2 numbers in the original, in the input, has 2 as the factor, right? 3 has 1, 4, 5 has 3, so forth, right? 10 has 2, right? So then now, the thing is that when we're trying to figure out the greatest common denominator, well, what does that mean, right? This part is a little tough. But basically, f of 10 is always going to be a subset of f of 2, right? Because f of because 10 is equal to 2 times 5, right? And so it is basically a combination of these two in some way. Not really, but it's just that 10 is going to be cannot be bigger than f of 2 and f of 5. And then the question is, well, what is, so in a way, looking back, right, this is the way that I think about it is almost like not prefix sum, kind of like an inclusion exclusion type thing, right? Which is that for this problem, we're trying to find GCD. What does the GCD mean for this problem, given this? The GCD means that if we're trying to figure out, okay, what is the GCD of 10, right? Or maybe the other way around, how many numbers together, or in this case, not even GCD, but how many numbers have 10 as the divisor, right? Well, the answer is 2 because we just did it. But how many numbers have 2? Well, we also just did it. But how many numbers have 2 as the greatest divisor, right? Well, in that case, you want to just do f of 2 minus f of 10, because the number of numbers that have only 1, 2, the number of numbers that only have 1, 2, well, you subtract it from f of 10, because f of 10 would be a subset of f of 2, and the numbers would not, go, right? And that's kind of the idea behind this problem, is that you construct all these things, you count all the numbers, and then the GCD, right, is going to be just that, right? Let's say you're trying to find all pairs of numbers where the GCD is x. Well, in this case, well, how many pairs of numbers are there, right? Well, for 10, we wrote there 2, right? So there are 2 numbers. Then how did I change thing back? There are 2 numbers for 10, which means that they're 1 pair. For f of 2, there are 2 pairs. Oh, sorry, 2 numbers of 1 pair. But 5, there is actually 3 numbers, which is 3 choose 2. So I guess also just 3 pairs, right? But as a result, how many pair of numbers have GCD of 5? Well, one of them has GCD of 1. One pair is already used for 1. So as a result, only 2 pairs have a GCD of f of 5. So that's kind of the way that I think about it. I think maybe if I were to do it again with this explanation, but we're already 10 minutes in, and if you, maybe I didn't, honestly, I don't think I explained this part that well, but if you were to start over, to kind of, if you were to look for a easier problem, but similar to think about, is that given x numbers, or n numbers, I suppose it's always n numbers, like give the GCD of all pairs or something like that, right? And maybe you could do a function on it, like for example, in this one you get the sum, but given n numbers, give the GCD of all the pairs, right? Like maybe you have in a list or something. But of course you can't actually do it that way, because then in theory there were n squared possible things, and then just doing it n squared. But let's say that give the sum of GCD of all pairs, right? Then we have what we said, right? Big sum of 10 is 0 to 2 times 5, 100 is right? And then maybe 45, like we said, we have and then I don't know, what's another number? I don't know, 33, I don't know, that's not a great number. What was another number? 48 maybe? So that's 2 times 2 what's 2 times 2? 24? No, 12. So that's, well, that's a lot of 2s is what I was going to say, right? Is that right? I guess that's right. That is a lot of 2s now. But in any case, yeah, that means that in aggregate, right, if you just look at the divisors, we have one, we have a 2, we have a 5, we have 10s, right? I guess this one's just kind of useless. I mean, it's part of the 3s. But, and then this one is also a bunch of 3s and 2s. But my point is that if you're trying to do pairs, then now you try to find the number of pairs. Instead of finding the GCD, you're just finding the CD, right? And then now you try to find, well, how many pairs have, say, 3 as the common denominator, right? Not the GCD, just the CD, right? Well, in this case, it'll be these three numbers, and three numbers, three pairs, right? You could, 3 choose 2 is 3 pairs, right? 5, we have, maybe this is a bad example, but also 3 numbers, so that's also 3 pairs. But then the thing now, right, is that, and as we said, in this case, we have also 3 numbers for 2, this is a terrible example. 2, right? We also have some at 4, if you will. We have 2 numbers at 4, right? And some at 10 and so forth. Yeah, we have 2 at 10. Yeah, but oh yeah, 2 numbers, which means 1 pair. Sorry. But then the idea that is the core idea behind this problem, though, is that, you know, the number of 2 pairs. Well, is it the greatest? No, because some of those pairs will be in this case in 10. Some of those pairs will be in 4. So you want to kind of dedupe, if you will, right? Because keep in mind that every number that's in that has a common denominator or divisor that has a 10, it's also already in 2. And once you do that, then we'll go over the code, but that's the basic idea, right? And then for this problem, instead of solving this problem, which I don't know if it's a Leetcode problem. If it isn't, then it should be. Maybe it is, and I always solved it. I don't know. But if you had this, then now you just have to convert this to the longest increasing subsequence, and that's basically the idea. Right? So maybe my explanation isn't that great, but here's kind of like the cliff notes, right? So for that, give the G's of all pairs, which is for the cliff notes is for each divisor. Calculate. I'm gonna just type this. This is dumb. I'm like writing slower than I'm typing, right? Hang on. Maybe I'll bring back the drawing in a sec, but I don't need it right now. Well, I'll bring it back for the LIS, but yeah. What did I write? Okay. So I think for you to solve this, I think the easier problem, and you know, if you haven't already figured it out, give the GCD of all pairs, right? Or maybe the sum, right? And as a result, then now for each divisor, the idea behind this core problem is just calculate the number of pairs that has this divisor as a common denominator, right? Or divisor. I keep on saying denominator, but I don't know. So it's not a big deal, right? And then, because you could think about this as like a Venn diagram, I think, right? I mean, that's how I thought about it whenever because I think it's set and stuff like this, right? But for example, what we were saying is that, okay, so let's say these are the pairs that are in f of 2, right? Then f of 10 is always going to be smaller, right? Like everything in f of 10 is always going to be here. Yeah, I think that's it. And then f of 5 is like here, right? I'm drawing this poorly because, okay, fine. Maybe I'll redraw it, right? Like this is f of 5, and then f of 10 is in the middle, right? For example, they're more like that, but the core idea is not even the f of 5 part, you know, that is relevant for reasons we'll see later, but it's the f of 10 is in the middle part, right? Because f of 10 now means that, you know, for example, if you have 10 and 20 inside, then now, yes, 10 and 20 as a pair will both be, you know, have this, well, not just this, but it'll be part of this circle and this circle, and as a result, in the middle circle. And as a result, if you're trying to just figure out the GCD, then now you only care about this part and not the part that's inside, right? And that's kind of the idea that is core to this problem. And once you kind of understand it a little bit better, we'll go over the code. We'll go over the code in implementation, but I want you to understand it and then see if you can figure out this one is an upsolve, or maybe it's not even an upsolve, because for this problem you have to know stuff like this. So maybe it's a progressive solve. Maybe it's a Leetcode problem. Maybe it's a code force problem. If you know, leave a comment. Maybe we'll link it out and whatever. But yeah, so that's basically the core part of it. And then now, this is the easier variation, right? And then now, as a progression, now we have to do longest increasing subsequence, which is kind of the same idea, right? Once you kind of have that background, which is given name numbers, LIS, right? Longest, or in this case, strictly increasing subsequence, right? And the idea to solve it is also the same way. For each divisor, calculate the number of strictly increasing subsequences that has this divisor as a common divisor, right? So we do it all of them, and also after that, then we are able to just calculate them in isolation because of the overlap and the set things that we talked about, right? And that's basically it. For the LIS, there is an O of n squared algorithm, right? But this is too slow, as we talked about. There's an n log n algorithm. There's a couple of n log n algorithms actually. Some with, binary search. Some with well, actually, I don't know if that. I think you can, but in any case, there are n log n algorithms. There's one with maybe binary search, but this one, keeping in mind that it's not about the longest subsequence. It is about how many in total, right? And we'll go over that in a second. But the idea is, is one way, and then another is dynamic programming. And then also maybe Fenwick dynamic programming, right? And that's basically the core part of this. I'm not going to go over the Fenwick dynamic programming in detail. I think there are probably videos about that already. Just because there is definitely a Leetcode problem, so definitely check that out. But I am going to go over it, just not in super long detail. Definitely, if you want to pursue it more and practice more, look over those older problems. And the idea behind strictly longest increasing subsequence is that you have some copy paste. No, there's examples are kind of crap. Do I have the drawing board up? Yep. Okay. Is that okay? Let's say you have some sequence, right? I don't know. I just kind of roll random numbers. But the idea here is that, so I'll go with the n squared dynamic programming solution real quick, which is just that, okay, how many subsequent n at 1? There's only one. How many subsequent n at 5? Well, we look at each one. There is each previous one, and 1 connects to 5, right? And as a result, there's 5, and then all the subsequence that ends at 1 and then 5, right? So, and which is, there's only 1, right? So that means that there are 2, right? And then 2, again, well, it only connects to 1, so there's only 2. Same idea with 5, right? Because there's only all these numbers that goes up to 1 and then 2, right? And then also, of course, just by itself. And then 4, it's kind of the same idea, or exactly the same idea, but now it's a little bit more visualization, which is that it connects to 1, which we said, right? So this is going to be 1. And then it also connects to 2, right? And 2 has 2 numbers, actually, right? So the two actually the two means that that means that all the numbers that goes up to 2 and then now add 4. So then there are 2 sequence in this way. And then just one that is 4 by itself. So this is 1, 4, there's one of them, and then 4. So it all connects to 4. And then same thing here. There are actually 4 different things, right? So another way to think about it, I mean, yeah, is that, well, now 7 is the biggest number so far. So you have 1, 7, yeah, which is going to be, you go to 1, right? You have 5, 7. It goes to the 2 sequence like that. 2, 7, 2, 4, 7, 4, and then just 1, which is 7 by itself. And then you sum it all up, right? 1, 2, 5, 9, 10, right? And then so forth. I mean, in this case, 5 obviously doesn't go to 7, and we don't even connect it to the second 5 because it's not strictly increasing. So then in that way, just add up 1, 2, and 4. So that's going to be 8, or was 7 plus 1 for 5, which is 8, right? And 4, you only add to the 1 and 2, so that's 3 plus 1 is 4. 2, just add it to 1, so that's going to be 2. 3 is 1 and 2, and the second 2, so that's going to be 5 plus 1 is 6, right? And then now, yeah, so that's the number. This is just the longest increasing subsequence, right? Okay, so the way that we did this is with dynamic programming, and this is n squared because we just look for every number that's smaller. But what if, but now that we have this idea, there are 2 things that we can do. One is that, well, 2 things that you have to do for this problem, but it actually comes up in different ways, right? But for this one, you need both of them. Which is, one is that, okay, all these numbers, I kind of made them small actually, but you can imagine one of them is like, let's say instead of 7 is 700, right? So that's too big. Or is it too big? Well, it is for the next part, but we'll just give you one hint, which is that we can renormalize everything, right? Because the actual numbers don't matter, just the relative numbers matter, right? Meaning that, as I said, I made this number 700, but it doesn't change the answer because it's still the biggest number. You could say the same with 50. Let's say you change both 5 to 50 and it doesn't change a thing, right? You get the idea. But as a result, we can map this from 1 to n, right? And the reason why you want to do it to 1 to n is that now then, wow, my 2 is really weird looking. From 1 to n, right? And the reason why you want to do that, because otherwise, honestly, it doesn't change the answer. That's the reason, is that it doesn't change the answer. But it enables you to do one thing, which is that now, well, let's think back to what we were doing, right? For a second. For 1, well, it's just the first number. For 50, we go previous number, everything that's smaller. What is another way to say everything that's smaller? Well, all the numbers from 1 to 49 in this case, right? And actually, let's skip ahead a little bit. We don't want to go over them. Let's say 700, right? Another way to say this, and after we indexed it, then now we are saying, okay, give me all the numbers that are from 1 to 699, right? But not only that, we're not even, we're drawing these edges, but we don't even care about the numbers themselves for this one. We only care about these things because we're summing them up. As you saw, for the 700, we're just summing up 1, 2, 2, 4, because there's 1, 50, and now 2, and 4 plus 1, right? So you have all these things that brings up to 10, which is actually, if you think about it, just summing up the counts that are at 1, 50, 2, and 4, and every number under 700. But if you re-index them so that it goes from 1 to n, what happens? Well, I don't know what 700 is. Maybe it's like 6, actually, because we use every number. But whatever, right? Let's say this is now n, right? What does that mean? Well, that means that now we get the sum of all the numbers at certain indexes. Well, because if we can get certain indexes, that gives us something called the Fenwick or the binary index tree, right? You can Google these things, maybe with better handwriting. But yeah, and what does that mean? That means that every time, like every query we will now say it again, which is that for 1 we go, okay, well 1, what are we doing? Well, nothing really. So then we just update the entry of 1 at 1, right? At 50, well 50 in this case is I think just 5 because we normalized it, right? So we just 5. What does that mean? That means that now we get all the sum of all the smaller numbers, and then we set this to, well, 2, because it's 1 for the sum of the previous numbers plus 1. And then now we have 2, right? We have 2. Yeah, same thing. Now we have 2, 4. Well, what are we doing? Well, we have sum up all the smaller numbers, so it's going to be 3 plus 1, so this is going to be 4. 7, which is 6, as we said. 6, we want it to be the sum of all the smaller numbers. So that's going to be, I don't know, probably 10 because we already did the math. I think maybe I'm 10 minus 1. No, that's right. 10, right? And then now for another 5. Well, what is the sum of the smallest number? Smaller numbers in general. It's 1 plus 2 plus 4. Right? So that's 7. So that's going to be 8. It's 8. But we actually also don't care about the per index things, though. If you do care, it's a trivial change. But basically now you just update this to 10, right? Because it's 2 plus 8. So then now, if for future use, if you need this, then it's just 10. And then 4 again is another 4. So now this 4 is now 8, right? 2 again is going to be now updated to 4 as a result. And then 3, finally, smaller numbers, it's going to be 5 plus 1 is 6, right? And that's it. And then now you sum all these up, and this will give you the number of longest increasing subsequence, right? And if you had keep track of indexes and stuff like that, you can certainly do it. And it may answer any queries that you might have for different type of problems. For this one, you don't need to, but you just sum up all this to get the number of subsequences, right? So then how do you tie this to this problem? Well, for this problem, let's say now you understand Fenwick and all these things, then now, instead of doing 1 to n on all the numbers, we just care about the numbers that has, well, as we said, maybe it just, for, I guess D for divisor is equal to say 4. We just get the indexes or numbers or whatever. I think it doesn't, basically you're just trying to solve LIS for these numbers, right? Man, I cannot type. Well, I'm not typing, that's probably why. For these numbers, right? Which has D as the divisor, right? I don't know why I'm writing. Sorry, let me get back to it. But that's basically it, really. I don't think I'm going to do any more visualization. But then, yeah, for each one, we just calculate the number of strictly yet as this as a divisor. We already wrote this, and we do it by what we talked about, right? We just keep track of indexes, and that's it. Yeah, a pretty tough problem, but now we'll go over the code, which is hopefully all the components that we talked about. Okay, and this is a binary index tree. The advantages is that it is relatively fast, but without going too deeply into it, you could see there is this add function adds delta to index I. This is going to be O of log n. That's the key part. N is the max index, I guess, right? And then some prefix, which is for sums all the values stored at index smaller than I think. It's off by 1, then you could change it to whatever, but that's basically the idea. It has the comment here, so I don't know, right? So I guess in this case it's actually, so we have to be careful, but it's fine. Yeah. And then the next thing is going over the code. First, mod. Max is the max number. It's so that we can get the divisor. I have this function getting divisor, though I guess you can also just do it once. Now that I think about it, I don't. Why didn't I? How come it doesn't show up here? Maybe I could get it to show up here. Does that work? Well, this code worked before. Now it's taking time. 9 seconds, which is a little bit sloppy. But actually, we probably could. Now that I think about it, you probably could take it out. But the idea here is that for the max number, which only goes up to 7 times 10 to the 4th, we want to get all the divisor. And how I do that is by using sif. Yeah, this is basically sif. But we can actually take it outside so that it only gets done once. I don't know why I didn't do that during the thing. I mean, I guess it's not necessary, but yeah, 7, right? And yeah. And you could kind of see immediately how much faster it is. Give it submit. I know we shadow max here, but everything's already filled out, so it's fine. I forgot what it was before. But yeah, okay, actually not that much faster, only like a second and a half, but still breathe a little bit easier, right? Okay. So then, yeah, basically the idea here though is that for each number, we do a sif to get all the divisor, right? Not gonna go over this. You can kind of trace a few iterations of this and you'll see what this does. But suffice to say, diff of j gives all the divisors of j. Is it? The other way. Oh, no. Yeah, this is right. Yeah. I just kind of. Yeah. Because by saying that every I, right? Yeah. And the reason why this is fast enough is that this is sif. I said that a few times with sif of. Yeah. I never know how to spell or even say errors. Okay, that's why I don't try. But yeah, this is there's a tighter bound, but you can say that this is max log max or m log m, which is why it's fast enough. Maybe it's surprising, but you can actually there are a lot of proofs on the internet, so definitely take a look at that if you're interested. But yeah, and then now for each number, we just keep track of. Okay, well for every number x, actually let me make this bigger. If only in life you can make things bigger so easily. But yeah, so basically for every x, we look at every divisor, right? And then we just kind of put it in a list. So every divisor d, we want to put I, which is the index, by the way, not the number. We want to put the index in it, and also put itself, because the way that we did the divisor, we don't put I and I just for off by one reasons, but as a result you have to put it there so that for example 10 has 10 as a divisor. That's what this is doing, right? And just keeping track of the indexes. Yeah, and then that's basically the setup. And then now we're trying to figure out as we said where the CD is G, right? Yeah, this loop just shows yeah, for every number that goes all the way up to max, we go number of subsequences where the common where the numbers have the divisor G, right? That's it. And we start at G, we have indexes, we have the length of indexes, and then we sort them. So this is the same idea actually, is that if you kind of look at the maybe I should have explained this first, but basically the idea is that if you have the indexes and you sort them by the value, then now you're also trying to find out the longest increasing subsequence of the indexes. You could kind of draw it out to see why this is the case, but the core idea is that if something is increasing, then that means that the order will be in increasing order, right? Because increasing order means that increasing order of the indexes means that it is gone in order. That's basically the situation. Anyway, we sort it this way, and the reason why we also tie break by -I is so that it satisfies the strictly increasing case, because if two numbers are the same, then it may not be, there's no tiebreaker as the indexes, but we want, actually as a tiebreaker, we want the later index to come earlier as a result. And yeah, let me add that. Sort the indexes is to set up for LIS, and this part is the renormalizing part, right? Normalize to 1 to some, not n necessarily, but let's say b, where b is the number of indexes. That's basically what this does. And then we set a tree, a binary index tree of that length. The length of the indexes b, and then for each one we just do what we said, right? Which is that first of all we get all the sum of all the smaller numbers, index -1. We add count +1 to it, also the same way that we already discussed, and then we just add it to total as well. I mean, you can also add the total later afterwards, and it's fine. But yeah. Anyway, and then now we set f of g is equal to total. So f of g contains the number of subsequence where the numbers has to divide, all the numbers have to divide as g, right? I'm going to pause a little bit to go over the complexity. How does this work? How does this work fast enough, right? Because max, you can say max is pretty big, right? I mean, it's not big, but it's still pretty big. So you do 70,000 loops. Each of these does, you could say n log n, but which is why I was trying to be careful. It's actually b log b. So you could say that this is O of m times b log b. But why is that fast enough? Because there's no, because m could be 70,000, b can be n, right? Because there are just that many indexes. For example, for g is equal to 1, that's every number for sure, right? Because that's just how dividing by 1 works. Well, the short answer is, as we said, for each m can have at most 128 divisors, right? That means that the sum of all m times b is equal to 128 times 70,000, say, which is equal to, I don't know what it is, but it's not that big, hopefully. 8 million, so maybe 9 million, say. I'll round it up to 9 million, which is going to be fast enough, right? That's basically the idea. And we have the times log b, but in reality, a lot of the numbers are smaller, right? That's basically why. It's just an upper bound, but that's how you kind of construct this thing. Yeah. And then at the end, and this is a critical part. So one of the reasons why I didn't get it at the end, or without like a little bit of help, is because I just kind of did the DP in the wrong order. I still think about DP, but basically this is to remove the common pieces, right? This is the f of 2. We want to subtract from f of 10 to get f of 2 uniquely, right? So something like that. Same thing that we talked about. First, for f of 2, we want to remove it from, yeah. So then for each I, which has, is f of key sorted? I think this is actually a little bit, maybe it is true, but maybe it's just a little bit lucky. I think it actually should be sorted with a reverse of true. But basically, and I talked about this already, but another key idea is that you don't want to double count, right? And what I mean by that is that f of 2, like it already subtracts from f of 4, f of I guess even 6, f of 8, ... right, all the way to. But the key thing, another thing to note is that though, f of 4 subtracts from f of 8, right? Or maybe not even that yet. But f of 4, if you don't do it in the right order, f of 4 contains stuff that is in f of 8. And as a result, you're double subtracting, right? Because f of 4, we haven't cleaned it up yet. If it hasn't cleaned up yet, then f of 4 contains f of 8 and f of 12, f of 20, whatever, right? Everything that's multiple of 4. So when you subtract it from f of 2, you're double subtracting the things that are both f of 4 and f of 8 because, well, f of 4 is not cleaned up yet, right? So you have this sort of double counting. So the key thing to note is that that's why I have to do this reversal, because then now you just do it backwards. Because then f of 8, let's say f of 8 is clean, then f of 8 contains unique f of 8 things, right? You clean it up, it's fine. And then when you do f of 4, then now when it subtracts from f of 8, then you know that f of 4 is unique, the f of 4, 4, which, no, in parentheses, number of subsequences with 4 as the divisor and not bigger numbers, right? And that's basically it. So that's why the order matters, but once after that, everything is also Sif, right? In the same way, which is that for every j, which is just what we talked about really, for every j that is multiple of I, we subtract it, we increment it to get the next multiple, and then now in total, now f of I contains uniquely the number of subsequences with I as the now GCD, so then you can add and mod, and then you're Gucci. And that's basically it. Again, I mean, there's some sorting, but after that, it is going to be m log m, so it is not that big, even though it looks scary with 2 for loops. That's it. That's all I have with this one. Let me know what you think. We'll show the code all over again. This is my binary index tree. Honestly, my personal GitHub thing was down, so I just copied this from ChatGPT, but I mean, it's a data structure, it's fine. And this is the divisor code. Also, like I said, it's just a Sif, pretty standard. I could write it like in 10 different ways. I mean, it is what it is. Definitely practice that if you cannot come up with that very quickly. And then this is just setting up the divisors and keeping track of indexes. This is LIS, right? I mean, this is LIS in a way. I mean, there are different variations, but in general, this is LIS with normalization and using BIT. Of course, there are number of longest increasing subsequence in the Leetcode problem set. Some of them are okay with n square, and maybe you even solved it with the n square way. But of course, if you solved it with n square, upsolve it using n log n. Even if you solved it with n log n, upsolve it this way with n log n. There are a couple of ways with n log n as well. So, yeah. And then, yeah, this part is just reversal at the end. And that's it. That's all I have for this one. Let me know what you think. Thanks for watching. Stay good. Stay healthy to good mental health. I'll see y'all later and take care. Bye-bye. Okay, some of beautiful giving into away nums of length n. There goes my hopes of going to bed early of my beauty sleep. All right, for every positive integer g, we define beauty of g as the product of g and a number of strictly subsequence of nums. What the? All right, mod, I guess. All right. What does this mean? You define beauty of G. Return the sum of beauties. Okay, so that means that we have one of order strictly increasing subsequences. N is actually only 10 to the 4 for some reason, but okay. Sum is interesting. Was that 70,000? Are you trying to bait me into a SIF? How many sequences of... Okay, let's say we go left to right. Well, it has to be increasing. Strictly increasing. So the order kind of matters, but okay, so let's say you have 3. What does that mean? So there's some like weird DP thing, maybe. I don't know. But look at it. Okay, let's say... I mean, it's 10 to the 4, so you can do n squared DP, but let's say you do a very basic DP, right? What would that look like? Well, 3 and 2, no bueno. Just add 1. Okay, so then all the previous numbers we processed, how many of them gives you a 1, how many gives you a 2, dot, dot, dot. So then it's just the number of divisors of... So you do want to do a SIF. But then it's not just that though, right? Because there's the increasing portion. So if it's just any subsequence, maybe it's easy. Well, I think it's easier in the other case. But it has to be smaller number. What does the smaller number mean? The strictly increasing means that the GCD cannot get bigger, right? Okay. If it's strictly increasing, then the GCD cannot get bigger. So then for each one, what does that mean? The biggest GCD for that number is going to be that number. And then, for example, there's also 1, right? So there's one sequence of 1, one sequence of 2. And it's only of numbers that are smaller, right? And you could walk the number that are smaller, can you? Walking the SIF. Remember, it has to be smaller, but yeah, I mean, something like this is kind of interesting. Okay, so then each number is, of course, itself a thing, and then it's 2 times 3. There's no way this is easier than Q3. I still don't know how to do Q3 either. I think I'm gonna come back to it. Is there any real people? I don't need this animation, you silly boy. You got in 3 minutes, so okay, let's go back to farm 3 real quick. I mean, Uri is very good, of course, but for a long time. I just didn't think that it would be fast enough. And with reasonable... Alright, well, at least we have time to play around with this one. Honestly, It's just a guessing game. This is ridiculous. I just kind of have nothing else to try. Okay, but at least we get to play with Q4, so that's always good. I don't know. I mean, the ideas, I think, you know, like, there are ideas, but for something like 4 and 6, right? 4, you have one number that's a 2. Is that enough for the 6 to pick it up on? No, I don't think so. I'm allergic to something. I don't know what's going on, but I'm gonna drink more protein. I've been losing too much weight. How do I deal with the increasing part? We could pre-process them in order. No, does that even make sense? So the biggest number is by itself, and then as it goes to the left, it can only go smaller. We don't have any idea on Q4. I'm annoyed at Q3. Honestly. I mean, there is definitely a SIF in here. Let's see what would that look like, or whatever. I don't know why it is such an odd number. 1, 2, 3, 4. Right. Something like this, right? And it's just part of the GCD. Like a small into larger type thing. How do I look up a small? Like, for example, you have 4 and 6, and then you do this. But what if you have 6 and a 4 even? How would you even handle that? Because the 4 you may type the 6. How is the strict increasing part? I mean, strictly increasing part. I don't even know how to handle the strict increasing part, even though I have a magic function to do the thing that I think I could do, but maybe not. Excuse me. Is there a thing on the level? No, the count doesn't matter, but for every one, then you just have a even if you have a dictionary on each one, we can't even afford to just look at the thing, look at each number. Right? And then also, let's say, yeah, how do you skip work? Like, what if you have 466? And you can't even dedupe them because you could have 4646 or something. And then now what do you do? Hmm. 20 minutes. Yeah. I don't even really have ideas. It's just maybe beyond my scope for today. What is the dividers? That's the thing, right? Like, for example, we have 4 and a 6. How do you figure? Okay, so let's say you just look at every divisor. So again, 70,000 biggest or most divisors. It's going to be 128 divisors. So actually, that's not bad. Why did I think this is going to be so bad? Is there an easy way to get all the divisors? I forget. Other than square root method. Okay, but let's say we have all the divisors. 128. Can I do it? Um, 70,000. What is square root of 70,000? 264. 264 should be okay. Actually, why am I spending so much time on this? Maybe I'm just conditioned to use SIF, but actually, okay. So, okay, what happens if we have the divisors? Then for each number, we could do dedupe, that's fine. But I don't know if that helps that much, but how do you even get all the smaller numbers? Your binary search on each one? That seems a little bit crazy. Can though, right? So you sort by the thing and then just keep track of the indexes. Binary search on each divisor. Even on each divisor is crazy, but okay. Is it just math? And for each divisor, which is a possible GCD. We count number of things that appear before us. But is that enough? Because we have to extend it out. Number of subsequence, it's not just the previous element. I don't know. So okay, so let's say you do check every divisor. What can you do? You check whether they exist. Because for 6, I guess in theory, you check for 2, and then there's a. I guess you could binary search on that too, but if you're going to binary search anyway, then you could just binary search on the number of numbers that are smaller than here. But then okay, so a number. But how do you count the number of things that where this divisor is the GCD? How many things? There's the increasing part, which is already tough. And how do you even know that? I don't know. Like, why 4 and 6 is 2, but what if we have 12 and 6? Why would you not say that is 2 or 3 and pick 6 directly? Inclusion, exclusion. I mean, I don't know, 128 devices is still a lot. I don't know this. Can you do number of primes? I guess number of primes is a lot less. Can you do inclusion, exclusion? Actually. Right, I guess I could Google that. Was it 70,000? What number has the most prime factors? Six primes? But that's six unique primes, right? 16 is the one, but 2 to the 16 for every number for inclusion, exclusion is probably too much. So 16 is too much. Okay. I mean, who knows with Q3 apparently working. So I don't know, but now I don't even know how to get the increasing part. Let alone, you know, all these other stuff. Why do I stay up till 5 a.m. doing this? All right, let's try what I said. I mean, we have 10 minutes. I'm not going to finish on time, but at least we can show some homework. Okay, so then now, okay, fine, right, so. I'm trying to figure out whether to mix it, whatever, same thing. Did I write this before? I do it on the same. I don't. Things are getting blurry. Did I already write this? I don't know. Okay, so then now we have this, right? And then we have. Maybe if. Oh. Okay. And then now, how do we want to write the other part? There are two ways to do it. One is by looking at the index. We could sort X by the thing. Maybe that's a little bit better, and then we look at the index. Either that, for each divisor, we store the biggest number, or just store the actual original number, and then just keep track of what is small. We have an actual count. I don't know though. Let me do it this way for now, maybe. And what we want is also I got everything look up. It's kind of actually I guess I could just do this. Okay, so then now we want to say for d in x, look up a div of x. So for each number we want to just say p of d dot append x, right? Maybe something like that. Okay. Well, I mean that's for processing, so I guess we have to do a little bit before, which is for d and x. We want to get count of. There is some. I still don't know how to do it though. Well, like I don't know how to get the formula, right? In the sense that okay, so then now we have p of d. Should it be a sorted list? I mean, yes, but I'm trying to think. That just adds an extra log. I guess it's not that bad, but it is actually. I mean, it's not that bad per se, but I think there's a lot of overhead. I mean, it's not. Right, and then now we can do a left of x. So all the numbers that are smaller is equal to count. But what does that even mean? I mean, okay, but I don't know, I have no time. Can I do something like this? That's not quite right though, is it? I'm just YOLOing, like trying random stuff. I don't think this is right in any case. It may even be too slow. Especially when, I didn't have an infinite loop. Do I? I mean, I must, right? Because otherwise this should not time out. Is anything obvious? Do remember the increment. Alright, well, can't do anything right today. This is the only loop, but why would it not get big? Is it this part? Oh, this part I forgot, and I don't use it. Alright, let's just get rid of those for now. Alright, good. I mean, I don't think this is right, but I'm trying to suss out, like, does it even feel right? Why? What do you think this is? P of D. Oh, whoops. Is either one or the other, but I didn't need to either. Okay, I mean, this is definitely very wrong. Also, I'm forgetting one. Yeah, okay. I don't even know what that means. So basically, I have 1 minute. I mean, this doesn't make any sense. I don't know what I'm doing, but it's just YOLO hope. But this doesn't even make sense, really. Okay, so this is the count, which is true, but I don't know how to take advantage of it. There's some like dynamic programming, maybe, because then now, okay, what am I actually storing? There's some, maybe? No, that doesn't. I mean, the count is the number of elements that are before it. Alright. Okay, so for each number, what does that mean? For each element, and these are all numbers that are smaller, so let's say the 5 of them, but it's not, because it has to be increasing, right? So you can only pick so it has to be unique, but I mean, we just ran out of time. Oh no, I forgot to take a picture. I guess I'll do it from my screenshots. But still, I hate how Leetcode does that. I just take it from my movie, but my video. Okay, but okay, let's think. Count is fine. Is it? How do you get the number of increasing things from just here, right? So it's already sorted. So let's say you have 5 numbers of the same divisor. How are you gonna figure out how many contributions there are? And also, like, the ordering of that matters a little bit. Well, I don't think I understand this one at all, to be honest. I mean, I think this part is fine-ish. It's either this or the sieve. I don't know. Don't I somehow mess up the sieve anyway. But this part, I'm thinking it more along the lines of DP, but I'm not really getting it. Unless there's some like crazy algo that I'm not aware of. Well, then I'm definitely not getting it, but it doesn't help me with this. And then the other alternative is to sort these and then And if you sort these, then you get it on the indexes. What does that tell me? Does that tell me anything different? I don't know. Honestly, I don't even have a great general idea. It's not even like I don't know, but I could grind it out, like yesterday's problem where I just couldn't get the formula, or earlier today or whatever. Okay, so this has 1, 2. What does that 1, 2 mean? And 1, 1, because 1 is always a divisor. That doesn't even help. Maybe there's some inclusion exclusion thing. Man, I'm not practicing enough for these problems anymore. And which would be fine, honestly. I would still do these if even for the cheaters, because it's just I should still be the same relative level, even if not solving these per se. I'm trying to also think whether I could do it the primes way, but I think that's like path dependent, which is a little bit awkward. Maybe. How will you get GCD from primes? Right? If you don't take the same path, like if one has 2 2s and 1 3, and then one has 1 2 and 2 3s, it's hard to kind of find the 6 together. But this way is not working either. Like, okay, so 3, fine. How do you even I don't even know how to set it up. Okay, let's go the other way of just giving track of the indexes. Does that even work? I mean, you still get the count the same way. I just don't know what to do with the count. Like, well, the count is also not the GCD. I mean, or D is not the GCD. It's just the divisor, which can be in a number of things, which is why I don't know how to do it. Like maybe there's a thing in which keep track of D in a good way or something. Is that it is the thing with the inclusion exclusion, I guess. Well, but in a DP kind of way, right? So maybe. So then now, yeah. So for example, we have 6. Then it's 6 minus 2 and 3, recursively minus the 1s, something like that. I could see it. I see. Okay, I think I get it, but that's kind of annoying to do, isn't it? So basically for 6, what do you want to do? For 6, you want to subtract out, okay, so you want to add out the number of 6 minus the number of 2 minus the number of 3 plus, I mean, in theory, but honestly not quite sure if I would do that correctly. But almost like inclusion exclusion type thing, but in a DP-ish kind of way. But no, is that though? I see. So then for each divisor, and assuming this is sorted, if this is sorted, actually that's pretty bad. I just forgot. Oh no, P and D is different. Okay, I was gonna say I forgot to sort it. Um, okay, if we sort, what does that mean? That means that we'll be going from a small number to a bigger number. The multiple paths. I don't know enough to about. I think the idea is probably maybe right, but with the DP, but I don't know how to do it. This is why you study. Alright, I'm gonna cap this for another 15 minutes. And then I'm gonna maybe pick this up again the next day or something. Really annoyed that I don't. I would say the good thing is that the extra time that I spent on Q3 didn't end up mattering, in the sense that I would not have gotten it anyway. But so I guess that part is good. I wouldn't have gotten this one anyway. I just don't know the math for it. I mean, we handled the strictly increasing part, but I think there is some, like, it's not this, it is that like, has to be something like, I don't know, right? And it's not just adding, maybe. It's whatchamacallit. I mean, you have to do, it's multiplying for some way. And you have to divide it under mod, so you do the modular inverse thing. I don't know. I'm gonna stop doing these at 5 a.m. Alright, next week I'm gonna get enough sleep. I was hoping that, yeah. I forgot what I was doing. So for each one of these, and these are all sorted. And now don't you have to figure out the branching? I don't know. Maybe not. Maybe I should add itself. I guess the way that I did it, doesn't matter. It should be count plus 1 maybe, but if you want to handle it that way for itself. Yeah, I'm not making any progress. I'm gonna call it a night. Can't even joke that swim. That's what I have. Yeah. I was gonna call it a little bit longer, but I think there's a knowledge gap. To be honest, which it is what it is. Um, I think I made good progress, but I just don't number theory stuff that maybe I'm a little bit shaky on. I guess I could also just review. Where's Alex? Didn't someone say Alex was there? TS Reaper is fine. Yeah, we'll take a quick look to see if it's something that I can even do. I don't know why they don't make these bigger. Like, what are you doing with the entire, like, more than half the screen? In any case, all right, that's interesting. I mean, this is like the factor thing. I mean, it's not factorial, but yeah, it's like the divisor of each number or something. It's kind of what I did, except for primes. Okay. I can read this just because, like, I don't know why they make it so, like, they spend all the money in the world just to make it impossible to read. Like in a way that normal people would read code, which is on a big screen. All right. Precision of. Oh, okay. So I mean, we did this. They did it by indexes. You could search on either one, I suppose. Okay. I mean, I had both ideas in my head. I didn't know which one. I mean, I didn't know either one. So, all right. We have the mod. We have this calculator function. I don't know what it does. What's calling this? So mx is the max number. I assume. Okay, so mx is the max number. So then we just f sub I is equal to calc sub I. What does that mean? Oh. Okay, so every number we do a calc sub I. We create for x in position of k. What? I mean, x is an index here, right? So for every index that has this divisor k, yeah, okay. So for each, okay. I mean, this was kind of the idea I was thinking of, but I couldn't figure it out. Oh, I see. I mean, I don't even know the rest of this, but I think this is kind of the idea that I was trying to think about, but I couldn't get it. But this was the DP that I was talking about with the inclusion. I called it inclusion exclusion, in a sense that you get all the smaller ones, so that I thought that you could do it multiple times though. So this is for every divisor. No. Okay, so for every I. Okay, so for every I, this is for every multiple of things. Oh, I was thinking of the other way actually. I don't even know all this stuff, so I'm probably still not right. So there's a whatchamacallit tree. Binary index tree. I suspect that's just used to count the number of smaller numbers or something. Actually, we could just read it, right? Oh yeah, this. Wait, do we use MP? Is MP the tree? MP is not the tree though. We push back. Okay, so for every number, oh no, for every, okay, so I mean, I was looking for this. I had it flipped the other way in my head, which is why I couldn't figure it out. But I think this the way this doesn't make sense, because I just couldn't figure out how to branch out and get all the divisors. Actually, I just did the math wrong, the divisors, to be honest, because I thought maybe I have to be a little bit stricter than this. Because even going up, I think I could have gotten it. But I think going down makes more sense in terms of that inclusion exclusion thing that I was thinking of. But okay, so you have a binary index tree here for every okay, so this is for every index, so we go, okay, so this is all the numbers that, oh okay, because they're merging from the back down, which I did not do. Okay, right, so then now p dot second is, what's m? M is kind of an incrementer, but how does that change MP? Well, this is P. Well, this is MP. That's this is a very weird. People write things in such a weird way, but yeah. Okay, so that means that for we sort the numbers. Oh, so it's just like, so this allows you to get the longest increasing subsequence thing, and then I guess this allows you to get, I don't know, what does this allow you to do? I mean, this is the binary index tree. Oh, I guess this is just to get the number of sequences. Yeah, okay. This is just to get the number of sequences that has, I guess, this k as the answer. Yeah, and then you want to subtract out the 5. Okay. I mean, I'm trying to think whether I want to, like, quote unquote upsolve this. Like, do I actually, like, I what I try to do in these things by looking at other people's code is not to copy the code, but to get enough of an idea so that I can implement it myself, right? I think the biggest thing I did not realize to do is that I was thinking recursively, but actually you only have 128 devices, but each of those 128 devices only have 128 devices. So it's actually not that bad if you're able to aggregate them in a good way, but I did not. I also kind of, so that's a thing. I don't know what this is. Oh, I guess this is, yeah. Because then now you do like a d square thing. 128 square maybe is a little bit big. 10,000 times 10,000 maybe a little bit on the bigger side. That's like 100 million, but a lot of them are not possible, so maybe that makes it a little bit better. But yeah, because you subtract out the bigger numbers in the count. But yeah, and that's how they get the prime shift is how they did the divisor thing. I did the divisor this way, but this prime shift or the factor shift makes sense as well. All right. All right, let's see if I can upsolve it, quote unquote, upsolve from my thing. I mean, I had a lot of the ideas. There's nothing that I don't know. So I guess that's good. But I think I wasn't able to kind of deconstruct the problem in a useful way. And here, what did I store? I store the numbers and I do them in order instead. I don't know that that's better or worse. Okay, so maybe I have this, right? And then maybe I have basically the idea here. Maybe I shouldn't try to make. I know that I'm trying to get my initial idea and try to make it work. Maybe that's not a great idea, to be frank. I also don't want to. Like, I feel like there are similar ideas that I can do that I'm exploring that are not exactly just another carbon copy of their code. And now I close the window. I try to not look at it until like I'm really confused again. But and we devise it. We want to say like, okay, I mean, I don't know why I wrote it this way. Maybe just write right, so then now f of d, so this is sorted, yeah, so then now it's equal to count, and then maybe we just do d, my previous d, but dp is too confusing. In div of d, but then we have to calculate this d. Yes, that's right. I mean, I think this will work, but it is too slow, which is fine. But okay, let's. I mean, I know that I'm doing it a funky way because I don't know enough to optimize it before knowing it. I mean, I guess knowing the answer, but we could get all the devices for the max number. Okay, so nums, right? And so then now we have for x in range of max plus 1, and it's just this part. I mean, I know that I could do it the Sif way, but for now, we'll just pretend that I didn't know the Sif way, right? I guess it's just this because we only can do it once anyway. And we go to side of 1. Right, okay. This is probably a little bit messy, but maybe I don't need to do all the number. Maybe I could do like a memorization thing, but let's not optimize anymore. Let's just see if we can get it at least correct, and then we can think about optimizations. Okay, and then now where we previous d f of pd minus f of d, right? So that we get, then those are not unique anymore, so we don't do this. And then now, okay, so this is the part that I mean, The reason why I didn't think about this is because during the contest, or even just earlier, I thought this would time out. So I was trying to optimize it, but maybe for now I just want to do it this way. Yeah. Do I need to add 1 to this? This is the previous. I want to add 1 to this for the current number that we don't add. Okay. I mean, even if we add it, it doesn't show up anyway, so it doesn't matter because it's the bisect left. So then now, yeah, for key value and f dot items, then now the key is the GCD, right? And then it's just this. I mean, I know that I'm too lazy to mod it, but I don't know why this. Oh, my output is ridiculous. I was looking at this, I was like, huh, that seems lucky. I don't think that's right, but how does this even work? I don't know. All right, so you could say print x. Oops. Print x. Oh, because I have too many negative numbers, and then it just gets modded. I see. Because all of the divisors, all the previous numbers should have or also have been, right? Because it's just like a not recursive. No, I mean, okay. I mean, I guess we'll print it out, but that shouldn't happen that we have negative things. That's the part that I don't get, maybe. Also, we shouldn't have 0. So 1, this returns 0. This for each. Something's a little off, or maybe a lot off. Should be 1. All right, let's read. Oh, because it has itself as the divisor. Because I'm a silly boy. Yeah, I mean, it shouldn't have itself. I was just trying to think whether it should. But because we start at 1, then, you know, we have these things. We just do 1. Okay. I mean, at least it is slightly better, but is it? Well, now it's subtracting it from 1, so that's, oh, it's because it was because of the number 1, and then it subtracts it from. Okay, fine. So 1 is a special case, maybe. So for all the devices, because it adds 1 and then it subtracts it from itself, right? So, well, okay. I guess we can write it this way. Start at 2 because this is silly, and then diff of 1 is just 0. Okay, is this better? I don't know, but we'll see. 1 should have 1. All right. This is very awkward, actually, because 1 is such a weird number. And I don't know if I should special case it because it's very awkward. But okay, fine. If okay, so if d is not equal to 1, I don't know. It's just very weird to do it. Okay. Now this is still wrong, just because. Okay, we fixed the 1. The 2 should, okay. It should have itself in here, I guess. It should have itself, but not here. I guess that's the thing. Eh. Okay, maybe that makes it fix it okay, and we just go back to 1. Maybe. Okay. It's kind of what I was hoping, so that's good. Not quite right though, but it's a start because it doesn't do the numbers quite right. And this still has negative numbers, which means it is very well, but okay. I mean, I feel like we made okay progress. Okay, so yeah, 2 goes for 2, and then subtract. Yeah, maybe the reason is because this way doesn't. We have to do all the numbers together, I suppose. Yeah, I mean, I see why people didn't do it this way. I mean, part of the learning and exploring is kind of figure this out. But the reason why people don't is because then now this doesn't make sense actually, because it doesn't do the previous number, so you have to do the numbers together. Okay, fine. Right, and how do I rewrite it? I mean, that part's not so bad. We should have a help before this. Also, I need to use the bathroom. Right, and now it's almost like DP, really. You get the contribution of each thing. Right, and now we process these one by one. Maybe. What are we doing? Is that what I want to do? Maybe process the numbers in order. Yeah, I don't know. Like yeah. Honestly, I remember too much of the other solution that I can do it, but I don't want to do it that way. But I don't know how to express this though, otherwise. I guess maybe it's just the idea. Alright, fine. Let's see if I can go to bed, if I have to figure it out. Okay, so then maybe you have something like, right, and then now we're saying that not only this, but for every factor divisor, right? Yeah, I mean, I guess you could do a if that way too. Just that for like something like this, right? Let's do it here. Right. I'm not ready to get this up yet. Okay, seems fast enough. So we have one or two numbers. Still fast enough. Okay, fine. Maybe I should think about using this more in the future. Okay, so then now x in thumbs. Then now for every diff of x, we want to say we want this number to be calculated for, as a possible thing, and then we just, I guess the subtraction is the only problem that I had issue with really. I for index. Yeah, okay. Right. Okay, right. And then now we're trying to count the number of subsequences where the GCD is this number. Yeah, I'm going to write G, but I guess that's not quite G over G lookup, maybe that's a little bit better. For G in range from 1 to max. How many subsequences are there with G, right? So G with all the indexes, right? Yeah, and this will be already be in order. So now what? So with all these indexes where they do have this thing, maybe I don't understand this part. I mean, this part was the part that I actually did struggle with the DP part. Number of subsequences where GCD is G. We have these indexes in order, right? We want to sort them by their value. Okay, no, that makes sense. So, okay, so, yeah. We want to sort them by their value, which is nums of it. Okay. So then now these indexes are sorted. Print it out real quick. Oh, I have spaces. Okay, so now 1, you have 1, 2. That's right. Should have a 0 actually. I don't know how to handle the 1 case. It's a little bit weird. They should all have 1s, right? One case is always very weird, actually. I don't know if this is right, to be frank. Like the number 1 and GCD 1, but I'll just try to focus on getting something right. For example, every number should be in here. So we have 0 and 1, I guess that's fine. But oh no, this is because I have this. I forgot that I put an extra case. That's why that's a little bit awkward. Okay, fine. All right. Okay, maybe that's fine for now. We'll see. Okay, so G, right? So okay. But this isn't quite right in the sense that okay, maybe that makes it a little bit right. Yeah. Okay. Oh, okay, so then now we don't need the 1 anymore. Okay, right. So then now this is just the number of numbers as we now go from indexes from left to right. This is the numbers of numbers that are smaller than it, because that's just how you do the thing, right? Okay. Yeah, that makes sense, because that is then now because you're summing up over. Yeah, that's why there's a binary index tree. I mean, I don't know if it's necessary, but I guess that makes sense. I mean, we'll do it that way. Let me find my binary index tree. And of course, my site is always down when I need it. Okay, I had to reset it, but for now, we'll just do something stupid and ask ChatGPT. Thinking longer for a better answer. No, just give me a clean code. Why? Why is this so? What the? Give me a basic. I have. The annoying thing is I do have code, but my server is down for some reason. Well, there's some reason it's because people are always DOSing it. Okay, but okay, we'll see if this is good enough. And this is from ChatGPT. I'm not gonna lie. We don't need some range. Some prefix is good enough, right? Yeah. So then now we want to say, okay. Binary index tree, I guess so. And what is n? Well, with G, that's too big, right? What's 70,000? No, 70,000 times 70,000 is too big. Length of indexes? Okay, yeah. Yeah, because then now... Yeah. What am I doing? Yeah, that's right. Okay. So then now we have for I in indexes, maybe just index in indexes. We want to go, I mean, this is basic TP, right? So from left to right, we go how many from the previous index. So then that's just tree dot some prefix of the index or index minus 1. Oh no, something like this, right? I guess it doesn't matter because index is not taken yet, so. So it should be the same. Right, so this is count as equal to this. And then is that good enough? Right? Okay, and then now we can say, yeah, for the factor of G is equal to total. I think this is maybe right. This should be right. Count is the number of thing, and then the DP of index is going to be sum of all those other previous things. Okay, I think that's right. And then the tricky thing is trying to get back to it, right? So which is, yeah, for same as before, really. For D in F dot keys. Oh, I guess I have an I here. I'm just looking at this code, basically writing the same thing but in a different way, slightly different way. This if, because then now we want F. This is actually reversed. We want this reversed. Because then now you can go F of I and then now this is the unique thing. So then total we added by, oh, this is another total though. Total. Just go T total. Then now we have F of J or F of I times I, and then just mod things, right? Something like that. Okay, what did I do? Well, some prefix. That's weird, right? I guess index can be 0. So maybe that just makes things weird. Okay, fine. Still makes things weird. Why is it going about? Oh, because this is the length of the indexes, but we're doing this on here. So we actually need to normalize these. Okay, that makes sense. That's annoying, but it makes sense. Yeah, okay, yeah. Yeah, function for this, really. Do I want to, how do I write this again? Man, what am I, oh, we're normalizing it. Sorry, it's 6:15 a.m. and I have not slept yet, so I'm slowing down a bit, but this should be a easy part of it. But I am, yeah. So, but because there's a lot of index and indexes and I, so I'm just like confusing myself a little bit. But so what I want. Oh yeah, okay. So then now when we sort, did I do it the wrong way? So when we sort, I am so confused. I think we can just do it this way. Let's just say we sort it, and now my computer's lagging for some reason. Why? Am I running out of hard drive space again? No, okay. Because my computer's just doing crazy things. Okay, so then now index is equal to I. Okay, so then now indexes is equal to lookup of index for index in indexes. Okay. Oh, oops. I don't know why my computer's lagging. I'm not running anything other than this recording thing, I don't think. Okay, I mean, rough a go. We could print F real quick. My eyes are already closed. Okay, so we have 3 ones. It's not quite what I want to hear. I don't know why these are zeros. Maybe this should be count +1 for itself. Actually, okay. I don't know if this is good, but it looks more promising. I don't think there's 6 ones though. 1 2 and 1 3, and also somehow that only sums up to 9. Oh, that's because it's pre-processed. So the 1 dupes on the 2 and the 3, but does it count itself? Handling the 1 is always so weird for me, but this seems okay. So that's actually, I don't know if that's true or not, but okay, we could get the final version. I mean, the final version's a little bit more interesting, maybe. No, we have to do it this way. Okay, so you have 4 ones, but I don't know how it is missing the 1 6 1 4 and 1 2. Maybe that's fine, but I don't know how it's missing the, well, which one is it missing? Dun, dun, dun. Okay, so for G1 is equal to 1, because this is, no, I mean, you could print it, right? Yeah, 0 1 2. So for 1, this would give us 6. 6 is 6, right? You have 0 plus 1 plus 2 plus 3, right? That sounds right. So, oh, why is 3 2? 3 being 2 may be wrong. Huh. Was that 2 before? Oh, no, that's not 2. That's index 2. Whoops. Okay. I'm looking at the wrong thing. Okay, I mean, okay. So 6 is right, 1 is right, 1 is right. But then now, for 1, we want to remove the 1 for 2 and 1 for 3. Do you? What am I doing wrong? Okay, so we loop the 3, delete everything. I mean, loop the 2, nothing, of course. Loop the 1. We have 6 sequences. Is that true? Even on dupes? Okay, 1 2 3 has. Why am I getting 6? Well, what does 6 mean? And what does the 4 mean? It's actually awkward. I don't know if it's the property of the 1s or something, but because the 1 subtracting out the 2 and the 3 makes sense, but the 6, so maybe my DP is wrong. Do we add 1? Or do we add count plus 1? Because it doesn't make sense, maybe? No, okay, well. Oh wait, maybe this is still campus 1 though. Cause then now, yeah, I don't know why I put 1. Okay, because that's the number of sequence that we add the current number to, plus 1 being itself, right? Oops. This is a very hard problem. I mean, I think, well, I guess we'll find out whether this is right or not in like now, so it doesn't matter what I think. But honestly, I probably just like copy 80% of it. But I forgot about this part being fast enough though. So that's a little bit annoying. And of course, getting the wrong answer is also annoying, but that's okay. We got halfway done. What am I misunderstanding? Okay. Let's see this thing first. Oh, maybe there's something to do with the unique numbers. I don't know that I handle it well. But I don't know if the overcounting is good or bad, actually. I don't know if I handled numbers correctly. No, because it overcounts here on the number of subsequences. Okay, that's an easy fix if true. Because then we have to do this. Because we sort by the number if it's deterministic, but or if it's what you might call it, not deterministic. What's the thing where it keeps the same order? Man, today I'm stable. If it's stable, then it keeps the I. But even if it's not stable, that means that there's a random chance it's not. So we have to make sure that we actually want to tie break by negative I, so that doesn't do it. Okay. Okay. I mean, that's actually. I mean, for me, that's a good sign. To be frank, I mean, not only because I was able to fix it, but that means that I actually understand it enough to fix it, right? Because if I didn't, then we'd probably just copy and pasting code. If it times out, maybe I'm okay with that. In the sense that 9 seconds. In the sense that it's not wrong. We have to do some optimizations, but it looks like we're okay, able to do without. I cannot keep my eyes open, so. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem, this contest, and everything in between. Stay good, stay healthy, take your mental health. I'll see y'all later and take care. Bye-bye.